Do you think you can move and sit near the front so it's a bit kind of cozy? It's not exactly an intimate room, but we can do our best. But if you sit scattered way at the back, it's kind of like, hello, stranger. And if you don't want to, maybe you can move off and have conversations elsewhere. That would be great. That's right, yeah. Get in or get out, that's roughly it. We'll start in a couple of minutes. You've lost them. And move it, do you want to move it nearer here? Oh, sure. Because we're all at the front. Well, you're still sitting near the back. Could you come and sit nearer the front? Yeah. No, humor me. Humor me. I know it's tough. I'm being horrible to you. Oh, there is fine. It's just that the whole group's near the front. Okay, this is good. So this is just a chance to, it's not often that, I can give talks about verse till I'm blue in the face, but it's great to have verse's actual, progenitor and creator here. And so this is your chance to ask Tim really anything about verse or epic or the metaverse. And I suggested to Tim we start with just kind of 3 or 4 or 5 minutes of general intro about in the context of what I said about, what are you trying to do, Tim?
Thanks, Simon, and thanks for coming. It didn't set out to make a functional logic language. Rather, we came to a realization that around 1998, that the future of 3D games and of programming in general was going to undergo a lot of really interesting changes. At that time, Java and C# had come out, and people were really starting to think about new ways of writing programs. But one of the really important ideas that influenced all of this was the realization that in the past we wrote standalone programs just containing our own code and maybe some other code we copied from elsewhere and stuck in our directories. But in the future, we'd have a medium where all of the world's consumers could participate as users and all of the world's programmers could participate as co-creators of software. In this world, kind of the model you might keep in mind isn't a bunch of separate programs that each are totally encapsulated, but a single world that looks to the outside world as if it were an infinitely fast computer running code written by millions of programmers and constantly evolving. And when we think about the metaverse, there's science fiction on it that's kind of dystopian, and there's a lot of marketing hype. But when we talk about the metaverse, we're really talking about social 3D real-time experiences. A lot of people getting together and having fun in a simulated environment, run on software written in a programming language. And so for a long time, we've all been thinking about how to build a programming language that's optimal for that. And one of the really important things for it is everybody's code is no longer isolated. It all needs to run together. One object written by one programmer needs to run and interoperate in the world with other things written by other programmers, even if they've never met, they've never tested their code together, and so on. And that all implies that we're going to need a really strongly typed system in which you can, by virtue of compiling code and see it doesn't have errors, find it's really likely to work in this open world programming environment. We want systems that don't break, because when you're writing code for billions of users, the cost of breaking is really, really high. And so that was kind of the motivating factor, to build a strongly typed programming language that was both easy to use, but also incredibly powerful. And that led to the realization that transactions are the ultimate concurrent programming model. You have network message passing and all of these other paradigms that have been used before, shared state concurrency, but really nothing will be as simple to ordinary programmers as writing what looks like single-threaded code and then using transactions and transactional memory, as developed in Haskell and elsewhere over the decades, as the paradigm for running lots of it concurrently when it's free of high contention. And so that led to a quest to figure out what are the right properties for a language like this, right? And it did not start out with a desire for functional logic, but a realization that we want to have the best type checker process possible, the best static verification of our program, so that we can catch problems before they occur. And so this began an exercise, I think I talked about at POPL 2026, to find all the ways that programs are going wrong, looking through Unreal Engine examples and finding just where things are breaking and how it's affecting users. And there are a lot of sources of errors, just like every time you access a pointer and you might get a null pointer exception or access random memory, and that's one category of problems. But there are lots and lots of other ones. And so we set out to systematically find them all and build a language that's optimal for that. And that led to functional logic. You know, there's tons of code that goes wrong because there's a condition that checks a bunch of things, and it runs a bunch of code that's contingent on those checks being sound. And you know, sometimes these things get out of sync, and that causes bugs. And so the ideal situation is, instead of having conditions with Booleans and old C-style control flow, to move to a model where you're in a condition asking a bunch of questions of the compiler and runtime, and if it's true, it's binding a bunch of variables which you can then access, and if those checks are false, then that causes control flow. And that's kind of functional logic with failure only. So you have success and you have failure, but nothing more. But that led to the realization that loops are kind of similar, except that they produce multiple values. So a loop with a filter is, you know, producing a bunch of values and then asking questions about it. And when you look at Haskell list comprehensions and monad comprehensions, people are doing a lot of really complex things there. They're extremely powerful. And so that led to the realization that, okay, the functional logic is a pretty interesting prospect for this, in that we can both handle success and failure, variable binding, control flow, and production of multiple values in a really composable way. And you know, whereas Haskell does this with monads, monads are great until you need to deal with a whole bunch of them that are nested together. And then you have all these monad combinators, and you're trying to get this thing into that format and that thing into that format. And a lot of the human confusion and difficulty of understanding and reading and writing code comes from composing all of these things, right? And so functional logic has this really nice compositional strategy. The idea is, if you want to, as a Haskell programmer, you want to think about what's happening in verse, it's like we composed all of the cool monads together into one uber monad. It's like Oleg Kisolyal's logic T monad and you know, the list monad and all of these other things. And then every computation is listed over that. And then we use an effect system on top of that to let programmers promise that in this place, I'm not going to use these particular monad effects. Then we do a type checking pass that does effects checking and things like that, which gives you a really nice way of controlling effects in a program in which a programmer never has to deal with monad combinators, just writing big, ultimately complex queries that can be like nested SQL queries that ask questions, gather data, and then handle control flow based on that. And that's why we ended up with functional logic. And then we also ended up realizing we want a type system that's really powerful and scalable. And there are a lot of type systems with strong opinions about things, and there's a lot of broken type systems in C and and other languages of this family, which don't go as far as they could. But there's also the ultimate type system, and you know you're on the golden path of type systems when you're in a system that extends all the way to proofs as programs, right? You know, the Curry-Howard isomorphism and the related realizations are that type systems are just a way of reasoning about what's happening in your program and saying what's true in your program. And that a program type checks is proving a theorem about the program. And if you construct a type system in a certain really powerful way, then you can prove absolutely any property that might exist in your program by manually writing a proof. And though normal programmers aren't going to write proofs of stuff, it's really nice to have this capability. And I think we're going to see really, really light proofs as program stuff, extending further and further into mainstream usability. But one of the aims here was to actually build a type system in a language that really comported nice with the type system that scaled all the way there. Because if you're not on that track, then I don't think you can say that you're on the evolutionary path towards the ultimate programming language. Right? And that's one of the things I try to ask is, like, say we met aliens from another planet and we started comparing things. We'd compare our languages. We'd have totally different languages, all for historical reasons. But when you look at our computer programs, I think we'd find like, we had a lot in common because, and we looked at our mathematics. I think we'd find we have the same mathematics. So one of the aims here is to figure out what are the artifacts of current human language and things, and separate those out from what are the permanent properties of mathematics and programming, and how can we incorporate them into a language in as simple a way as possible to make it as easy to read code and write code as you possibly can. And that's kind of Wirth's maxim, Nicolaus Wirth's philosophy is, instead of building a programming language with a lot of features, you want to build a programming language with a small number of features that all compose together in a completely orthogonal way, so that if you learn a small number of simple primitives, you can write incredibly powerful code, and it never gets more complicated than that. And that's why we ended up here. I think that functional logic is a way of compressing a whole lot of complicated features of monads and booleans and control flow, and all of these things into one new feature that might be new to you, but I think ultimately that feature scales better than the other features. And that's why we're in functional logic. And there's a lot of unrelated parts here, trying to satisfy different needs of game development, metaverse, ease of programming, and so on. And they all led to the current design of Verse. Now, we shipped a version of this earlier this year. There are thousands of programmers using it, and several $100 million Fortnite economy right now, and that will grow and grow. And we're ultimately working on a standards track to get this available to others. I just hope that the contribution of ideas is helpful to the programming language community. Anyway, that's way too much rambling. So we're here. I can answer absolutely anything about Verse, why, how, or Epic Games or the game industry. I guess this isn't Ask Me Anything, so you can ask about my pets or whatever.
Good, so just go to the microphone. I must say, I haven't heard that before, Tim. I love the idea that when we meet aliens, we may not be able to talk to them, but they'll be programming in Verse. So let's start with Sam. You got there first.
I had to ask this question because you talked about the problem of monads but not composing well. Have you thought about effect handlers, which do compose well?
Fancy that.
So let's see. I see effect system from the point of view of a practical programmer. I see a small set of effects features that are extremely general and very commonly used by all programs. And that's what we try to do incredibly tightly in Verse. And then I see an extensible algebraic effect system research that lets you do more and more. That adds complexity as you go. But we're just right now trying to nail the solid starting point for that. What are effects? Effects are I/O and reading and writing memory, which becomes really important and significant with transactions. And effects are throwing exceptions and catching them. Effects are also potential divergence. Partiality is an effect. If you want to have a proofs of programs language, you've got to have a total programming subset that you can type check, and so on and so on. So we're starting very small, but I think the design of the language is so that you have effects polymorphism and higher order effects. You can pass effects into a program and compose a function out of them. So I think our aim is to support everything that could be supported in these effect systems.
Does that mean you may add something like user-defined effects via effect handlers in the future?
Oh yeah, absolutely, right. Absolutely. Okay. I would hope that in the future you could write something like Verse doesn't implement any of the sort of Rust linear type system stuff of borrowing and checking usage of variables and linearity. But I would hope that you could add that in the future, purely through abstracting within the language.
Thank you.
Let's go to Anil.
Hi, Anil from Cambridge. So this is shipping in Fortnite, so there's a good chance that this is now the first language that kids learn, and it's going to be a functional logic language. How do you think this, in contrast with things like Roblox and stuff, there's all kinds of weird and wonderful dirty code with no security models flying around, does this affect how we're going to teach kids computer science and get them excited?
Well, I sure hope so. One of the things we've talked about for a very long time is we want to make programming as fun and cool as possible. Something that your school forces you to learn isn't that cool. Something that you want to learn on your own because you can make cool things happen in Fortnite by typing code is an incredibly valuable thing. And this is why we really went to a massive effort. And angered a whole lot of old school C++ programmers at Epic in order to make the language as close to mathematics and algebra and the things that people are learning in school as possible. Like followed Professor Wirth's advice to use colon equals for definitions and equals for equality and no double equal sign and so on, just in order to, so that the symbols line up with what people learn in education as much as possible. But ultimately we want to get to the point where anybody on any platform, including mobile or console, can go type in some code in verse and make it run in the game environment and have it run in a really simple way. And there's a lot of other scalability issues in the metaverse associated with that. Security is a really critical one. The Roblox programming model is Luau, a kind of weakly typed language that's gaining some typing extensions to it, a la TypeScript. But it's another language where you can access everything that's in there and send data off to any server and everything. And to the extent that data might be people's birth dates or other private information, like that's actually a problem. So we see the type system in the language as providing security guarantees. It's a really, really critical part of that and a part of making programming accessible to everybody, not just licensed professionals.
Right.
By the way, Alan Jeffrey, the author of Luau, is sort of out in the audience somewhere there. So, hello, Alan. Please.
Conveniently, I was about to ask about security. In particular, one of the things that you see in a lot of the security type languages is the ability to do things like express policies, like you, Tim, are my friend, and I want you to be able to see my information, but I don't want Nikhil Swami to be able to see my information. Is that something that you're planning on supporting in verse? And if so, what's your general approach?
Yes, absolutely. Security has been at the forefront of all the thinking on this for like 20 years. Like, embarrassingly, it took us 20 years to ship this thing. But right, so there are various approaches to it, but the verse philosophy is very much statically verify as much as humanly possible. And when something needs to be done dynamically, there's always going to need to be an escape mechanism to ask if you're allowed to access something or whatever. But do that in a way that respects the security and the long-term extensibility guarantees of the language. And so security, it turns out, everybody's familiar with Philip Wadler's paper on universal properties and parametricity. Basically, the idea that there are some data types that are so big that you can't actually do anything with instances of them, like theorems for free?
Theorems for free, I think that's the paper you're talking about, yeah.
Yeah, but the idea is if there's a top type in the type system, like a type that can contain any value of any type, it doesn't expose any operations on it. And so if you're given a value of this type, you can receive it, you can pass it out as a parameter, you can do anything with it, but you can't ask any questions about it, you can't access data within it. And that's kind of a foundational security primitive. To have information that you can circulate around without asking questions about it, that's a security property. And so we very much embraced that. And we very much tied the idea of security, what you're allowed to access and what you're not allowed to access, to the open world type system and extensibility guarantees. The idea, one of the ideas is that a module can contain private variables, things you're not allowed to access. You can't ask if a module has a given field with a certain name. The fact that you can't ask that question in verse both guarantees that a module that doesn't contain that now might contain it in the future, and extending the module to contain that field isn't an effectful operation. It's something that does not break any observable property of the system that existed prior to it. So we have this dual purpose of a strong type system serving security needs, and we're really working to ensure that that whole thing scales to the large scale of the metaverse, so that lots of user modules can be running in the metaverse, maintaining confidential data inside of them in a way where the type system guarantees that that confidential data can't escape to be observed by third parties.
Okay, great, please.
Hi, Katie Casamento from Portland State University. So I have kind of a question about, I suppose, marketing and kind of how you are selling this language. I cannot resist taking the opportunity to say I love the old Jazz Jackrabbit games, and I would love to get those soundtracks on vinyl records someday. But my actual question is, Fortnite, and I'm not I think I'm a little old for the demographic, but Fortnite is obviously a very, very mainstream thing. It's very, I mean, I know about it even though I don't play it. And functional logic programming, I am very interested in it. I'm a fan of it. I think it's fair to say it is a non-mainstream thing right now.
I think that would be fair.
Yeah, so I suppose I very much do sort of buy into that, you know, if we get new programmers learning this as their first language, that could be a wonderful thing for the future. I'm curious about the sales pitch to existing programmers who maybe are not as nerdy as me about programming language design. As somebody who's a C++ programmer, a Python programmer or something, how is this, how are you sort of selling them on this? Or maybe we don't need them if the next generation is going to replace them eventually.
Well, you know, it's a funny thing. A new language that tries to shake things up is actually a harder sell to existing programmers than new ones. And you know, it's a harder path. Once you've been spending a decade or more programming in C++, it's really annoying when conditionals come in, and when you don't have Booleans, and if statements don't work like they worked before, and now everything's, you know, functional logic. And so there's always initial resistance to that. But you know, it takes a few weeks of coding to get beyond those frustrations and just to be able to crank out code. But you know, the most hardening part of this whole project was, you know, in a functional logic language, a lot of aspects of the Curry-Howard isomorphism, you know, the equivalence between logic and evaluation in a programming language and type checking in a programming language, just like naturally holds. And most people actually amazingly have an intuition for this, and are starting to write code. Like I saw, you know, I went onto the verse forums where users who are learning programming for the first time or switching from Luau or whatever are writing code and sharing it. And they're writing some really sophisticated conditionals. They're like, it's just second nature to them now to like do a test, bind a variable to some complicated nested, you know, calculation on arrays and containers, which might fail anywhere in it, and just be like, oh, if this whole thing succeeds, then we have these variable bindings and we'll use them else, and then go off into control flow land. And like, it's actually taking the C++ programmers a longer time to start writing that code because they're just like grumpy and frustrated that they can't write it the old way, and the new ones are just like picking it up as second nature. And I think it highlighted a lot of really early memories. I started programming when I was 13 on an Apple II, and I just remember all of the things I typed. I thought, like, I'm really smart. I know how to do this. This works logically, and it didn't work, right? You know, I wanted to write if a equals 1 or 2, then do this thing, and it didn't work. You all know why. So that didn't work. So I was like, okay, I guess I need to parenthesize that. If a equals parentheses 1 or 2, that should work, right? Well, that didn't work either because it all collapsed to a Boolean and everything broke. But like in a logic language, it actually does work that way. In a lot of aspects of human language that we've learned and use intuitively and that we kind of look to when we're learning programming actually works much better in a functional logic paradigm. So like I think the educational aspects of it and the learning aspects will be great. And I think for the other programmers, you know, the real pitch is that the metaverse is going to need a new language because an unsafe language just isn't plausible. And taking an untyped language like JavaScript and trying to scale it up to the metaverse where you have billions of users in a concurrent system that's completely untype safe, you know, I think everybody realizes that that sort of thing is going to collapse under its own weight. Some programmer is going to publish a new version of their module that breaks everything in the metaverse, and now 3/4 of the metaverse is broken. Like, no, we need type safety, and you know, and we work back from there and realize that, okay, we're going to actually need to rigorously define a new language, and it cannot be the web standard language that we have now, because that just isn't going to scale this way.
Sounds good. Thank you.
Ben?
Great, Ben Gamari, well typed. And a few times so far we've discussed, you know, ways in which programs could go wrong. And of course, one way which programs can go wrong is that they take much longer to evaluate than we would expect. And it seems like in verse we lose one tool for reasoning about that. That is, you know, types which tell us how many of something we're referring to, right? Now we have this notion of non-determinism in the language and ordered non-determinism with that. So you might not even be able to use parallelism to evaluate those many values. So that kind of is an interesting proposition, right? Now we functional programmers sometimes have to defend ourselves against imperative programmers who claim that performance predictability is somewhat lacking in some implementations of these languages. What do you think the? What are your thoughts on that? How are we going to understand the performance and runtime of verse programs?
I think the neat thing is to realize that the translation from a verse program to a language like Haskell, translating from the verse everything monad, we're using some subset of the effects to the Haskell appropriate monad composition, is actually a very simple mechanical process. And the verse version isn't going to do any more work than the Haskell comprehension would do. And this idea of choice is all designed so that you can always short circuit it out if the semantics require it. Like if you ask for just one of this giant expression that might produce thousands of items, it'll just start producing items one after another until it finds the first one that succeeds, and it's done, and it cuts, and you go on. So there's no inherent additional performance loss in this sort of system, at least not any sort of combinatorial performance loss. But I'd say from our experience, I don't want to credit verse for this, but when you're in a language with an effect system and libraries and user code that are using it to a pretty adequate level, it's vastly more, a compiler is vastly better able to understand what kinds of optimizations it can do in order to optimize the program. For example, a for loop, though the choice operator is sequenced, it says it has to produce this one and then that one, this element then that element, because if you're forming an array, the order matters. If all of the logic in the for loop is just producing an element, then it just looks like a Haskell list comprehension. And if the expression that you're using to produce these elements has no side effects, then you could run it concurrently, and that can just be a compiler optimization. So we can use the effect system to instruct the compiler on how things can be optimized back. And in general, I think the lesson is the more we can statically understand what's happening in the program at compile time, the more the optimizer can optimize. And the verse verification paradigm, like here's a future talk, ICFP'23 perhaps, on verse verification, but there's really a huge amount in a language that's structured exactly as verse is. There's a huge amount a compiler can recognize and understand about the language that's generally not possible in C++ because in the presence of open world constructs, you just can't predict what effects things might have. So I think optimization will be a really exciting project, and the compiler team at Epic working on this came from JavaScript, and they really love the new constraints the language imposes that enable optimization.
Thank you.
Yeah. Great. Okay, Will.
Hi, Will Creighton from Brown. So the last time we tried general purpose logic programming was Prolog, and it didn't work out super well. At least it didn't find widespread adoption, and to my understanding, that's in part because A, people found it difficult to encode the problems they had into the primitives of the language to express it as a logic program, and B, when they started to care about performance, they had to use all these operators like cut and so on that required them to think about the details of the implementation and sort of lose the declarative promise. And so I'm wondering how you feel the elements of Verse's design will help Verse succeed in the way that maybe Prolog did not.
Yeah, well, there was Prolog, but that was the tip of the iceberg of the 5th generation language effort, which tried to elevate, kind of combine the idea of logic programming languages with the early idea of the time of AI, which is not the same thing as it is now, but they tried to combine that to create a future generation of languages that would be way more automatic, faster, and more magical in its ability to generate code or solve problems where you just specify the problem to be solved rather than the algorithm. And I think that failed because they aimed way too high. On the other hand, let's look at something that has succeeded in all of these languages. Languages have added ever more constructs for dealing with data that might be absent. Null folding in C# and these other constructs, or null propagation. We have operators in various languages for that. Every language since that time frame has adopted list comprehensions at least, and some more, much more, like monad comprehensions in Haskell. And so like the way that programming languages produce and consume lists and deal with like coroutines and other ways of producing lists and producing things, consuming them, and composing all of these operations doing that thing has gotten better and better. And so with Verse, we're really aiming just at doing much better iteration and much better conditionals. And by providing those two primitives in a way that encapsulates really nicely, In Prolog, you write a top-level program, and your one functional logic interpretation of all of the choices and cuts and things happens just at the very top level. Whereas in verse, every conditional statement is its own little context that you're like kind of working out on its own. Every iteration statement is doing its own little functional logic loop within it, but then you're consuming the results in a totally normal program. And so verse looks very ordinary when you're writing code in this. And if you look through the code that people are writing in Fortnite, it looks like C or C# code, except they're doing a little bit more with conditions and a little bit more with loops. And I think that's a good starting point. And over time, we'll have more and more, like one of the magic of bits of functional logic is that you're able to run functions backwards under certain conditions, solve for the parameters in terms of the results, and so on. And I think we'll get some benefits of that, but even if we just use this little subset of functional logic, it's still making the ability to write really interesting nested query expressions much easier. And I wish I had another 10 minutes to present in the topic on exactly that, but it's just really magically simple to write conditions that ask complicated questions without having to use monad composing.
Here's one other thought too, that kind of to respond to your question, which is that functional programming has proved more sort of durable and popular than logic programming in the sense that you're describing. But functional programming is just a subset of verse, right? Every lambda calculus program is a verse program, right? So there's all of that goodness and some more besides. So so that the higher orderness, having native higher order is very important, right, to functional programming, and that's all part of verse. Please, over here.
Hi. Jeff Henriksen, GrooveScale. I'm interested in graphics, and I'm interested in GPU and GPU-like devices as a precedent for where is the world going after Moore's Law is over, now that it's over. And so is verse about graphics or GPU-like devices?
Well, the long-term aspiration is for verse to be a candidate everything language, or a general programming language. Remember the movie about Alan Turing said, oh, you're trying to build a general computer. Well, but we're trying to build a general programming language, and I don't think any exist yet, right? Because you have a bunch of low-level ones and a bunch of high-level ones, and some that are good at graphics and there are other things. But I don't think you can look at any language that exists today and say that this is a general programming language yet, because if you don't have a proofs as program system, then you're lacking a massive swath of computer science. It's going to be very important for robust programming in the future. So if you don't have that, you're not an everything language. If you don't have the ability to just write ordinary code of all types that are used in all applications, you're not a general programming language. So really aspiring to be that. And having an effect system in verse is nice. A lot of the constraints that are placed on graphics programs, like CUDA programs today, that enable them to be ridiculously optimized to run thousands of times faster than they'd run on a CPU, are limitations on the effects they can have. And by extending the verse system, effect system, I think you could actually capture that in a way where you can write massive libraries of functions that are guaranteed to be vectorizable onto a GPU and run at full GPU performance. So I think there's a future there. It's not a focus now, but I think any language that claims to be an everything language is going to have to address a wide swath of problems that I don't think anybody's really thinking through fully yet.
Thank you.
Okay, good. We're now we have 8 minutes and 8 questions, so we're now into speed dating.
Okay.
Okay, all right. So, Oliver first.
3 minutes.
Oh, 3 minutes.
Okay. I'll ask my question really quickly.
Rich, ask it quickly.
Okay, so Scratch and these other things, and Unreal Engine's scripting language, which lets you drag boxes around, have been really successful for teaching people programming and getting people off the ground. I really like these structural editor thingies, this sort of thing. Are there any plans for some sort of editor that will allow people to quickly get started, or even continue programming and never see any text?
Yeah, it's coming. We have a prototype of visual verse up and coming. It's like Scratch. It has the property that you can snap these blocks together in ways that guarantee that the code is going to work and is structured correctly. But if you just go through and literally read what looks like text in the blocks, then you actually have a normal verse program too. So I think that's going to be a great educational tool, and will make programming, especially introductory programming, more accessible.
It's exciting. Thank you.
Great, thanks.
I'm afraid my question might be long. I'm Catherine Phillip from Portland State. Back into performance stuff. From my elementary knowledge of functional logic programming, there's performance is still, like to make the choice operator performant is still an open problem. But you claim that like it's not going to be like any slower. Like how are you guys achieving that? Is there something like particular with like this design of first that like avoids the conventional problem, or you guys are tackling it as like an engineering challenge to like solve these problems?
Well, with functional logic and choice, what you're really looking at isn't functional logic over the entire program state for the entire world. What you're looking at is like an if statement or a for loop, which is doing some iteration within it. So it's always delimited, and the delimitation is usually pretty small because your program's usually doing pretty reasonable things. And so one of these choice expressions that looks like a normal Haskell list comprehension should run about as fast as a Haskell list comprehension. And though you have the capability of doing some more sophisticated things, it's relatively uncommon, and I don't think it would be any more expensive than if you wrote your algorithm out longhand without using the functional logic features itself. Because it should just translate, basically versus lambda calculus plus choice and unification and existentials. And those three new features, they're nice for expressiveness, but they can always be collapsed down to regular code generated by the compiler that doesn't do particular crazy stuff.
Time for two more, do you think? Yes, okay, go.
From
yes.
Awake Security. So I'm curious in terms of philosophy of language design. You've got a language that's designed in particular for the metaverse, which is a place which is, you're describing things that exist within a location in the virtual space, and it's metrizable, and they have distances, and all of that. And I'm wondering if that target environment for the sorts of code that people are going to be writing, at least at first, has informed how you're designing the language and the boundaries of modularity in interesting ways. I'm thinking especially STM here, but there may be other ways too, so I'm open to hearing what you have to say.
Yeah, so there are two scalability challenges for a metaverse language. One is modules of code written by different users. The idea is you publish a module, and as you publish updates to it, you have to guarantee and be able to statically verify that your new module's interface is backwards compatible with the old one, so you don't break anything that exists, at least at the interface level. And we have a nice structure for that, that's just a matter of designing a type system and feature set that's really nice for open world extensibility and encapsulation. Java and C# have some nice backwards compatibility rules too. We just go a bit further. The bigger challenge is going to be STM. Like, it's completely unproven whether what we're trying to do here is actually feasible or not. Build an STM that scales to a billion user concurrent system. But the one thing that's absolutely essential, this can only succeed if you have a huge degree of data locality, that like a few objects interacting together in a small space may have interdependencies which force their updates to be sequentialized. But it absolutely must be the case that random objects that are unrelated to each other must have a very, very, very low rate of read-write dependencies between them, so that the STM can actually run stuff in parallel and retire conflict-free transactions. And that's a data structure design problem and a logic design problem, but I think, and I have a high degree of confidence it works in general. A whole world of people, like each of us here are not affected by people in other buildings in this area. And I think in the code version of us, that would be true also.
Thank you.
Okay, actually, I'm going to ask Jeremy to ask the last question, if that's all right, and then we'll close.
I'll be outside. More questions outside.
Yeah, that's right. We're not running away. You're not running away, right? Yeah, okay, Jeremy.
Jeremy Gibbons from Oxford. You mentioned starting programming at 13. How did you get from there to Curry Howard? What was the gateway drug?
It was a bunch of formative experiences, but I shipped my first game in 1991 to the public and started making a little bit of money from it, grew a company, and the 3D gaming revolution took off, and eventually I figured out how to do 3D. We put together a bunch of our small independent 2D game making teams to 3D, and built the first Unreal and shipped it in 1998 with a little scripting language and other stuff. And at that point, a lot of these foundational thoughts came together that networking should, in a 3D environment, should be automatic. You should be able to write just normal code, and then the way the simulation is distributed among clients and servers should just be automatic, right? The system should do that, not the programmer writing the individual code. That led to the realization that transactions were the ultimate solution to this. It had transactions on my to-do list in, I think, 1999. We're still working on them. But it's really clear that programming languages are very much a bottleneck in the evolution of software. Just as Moore's law, hardware performance and programming languages are dual bottlenecks, and some problems are only solved with brute force and Moore's law improvement, like the AI revolution. That's just flops, nothing more, and some awesome research. But programming languages are the bottleneck, and as long as programmers are having to write shared state concurrency, they're never going to write programs that scale up to hundreds of cores. And as long as we're using network message passing to negotiate what's happening in a 3D world, we're never going to have a billion-user simulation. It's just going to be too hard for every programmer to write code for that. And so we kind of viewed programming language improvement as a necessary step towards building much better software systems. And I still believe that's the case today. Nobody's built a major game that's gone more than 10,000 concurrent players that hasn't been a real scalable system to lots of programmers.
Thank you. Okay, thank you. Well, we got to wrap. I think you can see. Thank you very much, Tim.
So this is the final session of ICFP 2023. I thought that was a great way to finish up. I hope everyone's enjoyed the program so far. So thanks to all of the speakers, all the keynotes, the people who did the fireside chat, and Tim to finish things off. Thank you very much. And as Nick said, there's plenty more events in the coming 2 days, so enjoy.